Hi, I'm Carlos Merino, a student at the Polytechnical University of Catalonia in Barcelona and also team member of MotoSpirit. Please, come in. MotoSpirit is a student racing team that designs fully electric motorcycles that take part in the International MotoStudent Championship, a competition that gathers university teams from all over the world to race each other and find out who is the best. But today I would like to show you all the designing process of a motorcycle swingarm. The swingarm is one of the most critical parts for us. In fact, the behavior of the bike is mainly determined by its geometry. And of course, since it is the connection between the road and the bike, it must withstand great forces and momentums. But the problem is that being such a big component, it is crucial to make it as light as possible, so we don't lose any time on track. Luckily, we can do exactly this, thanks to Altair Inspire software and its topology optimization tool. Let's go to the computer and I'll show you.
Alright, so here you can see our 3D model, and first of all we're going to make some partitions in the swingarm axle and now in the suspension system holder. Then with the help of the cutting tool we're going to make some more. Now we are selecting our design space, and that would be all the preparation our model needs. Now it is time to add some supports and forces. For example, this one is generated by a suspension. And these are both the component of the forward and normal force of the bike. On the other hand, this is the force produced by the chain of the bike, and actually it is the biggest force we will apply over the swingarm, at 12,000 newtons in total. All of these forces are related to the maximum acceleration scenario, but I will also create two more scenarios, one for left turns and another for right turns. And just like before, I will add all the necessary supports and forces for these new cases. More specifically, these are the forces that the motorcycle experiences when turning right. And obviously, the left turning case is exactly the same as this one, but mirrored. Now it's time to add a couple of fasteners in both axles, to make the model as close to reality as possible. As for the material, we'll be using this aluminum alloy, which is commonly used in SLM, or selective laser melting, the method we are going to use to manufacture our swingarm. In addition, I will apply a split draw direction to the model. And finally, everything is ready to start optimizing. I'm going to conduct a topological optimization with the purpose of maximizing strength. And after some trial and error, I've discovered that a target of 30% of the original mass is the best option. On the other hand, for the element size, I will select a minimum of 16 mm and a maximum of 32. It will provide a perfect balance between precision and processing time. And last but not least, I will use all the load scenarios I presented before. And there we go, we have our optimization running. So, after waiting for some time, our optimization is ready. Here we have it. As you can see, it is truly unique, and its shapes are fascinating. And by the way, it's not symmetrical. The reason being that the force of the chain is mainly applied over the left side, making it thicker. And after some polynar streaking and rendering, this is the final result. And now onto the good part. How good is our optimization? Well, let the results speak for themselves. After conducting a von Mises stress analysis on the original and optimized swingarm, it is obvious that the first one is way too strong, especially given the fact that the material we are using has a yield stress of 200 megapascals. In the same way as before, we can see that the original swingarm has a way too big safety factor, and the 3.5 the optimized one has is more than enough for us. This is when it gets interesting. With a final mass of only 3.7 kilograms, we have managed a staggering 70% weight reduction. And that's it. Thanks to Altair for giving me this opportunity, and thanks for watching.